Hey, it's good to see you guys. Welcome back to your favorite Calculus 1 class. We're going to look at one-sided limits. And if you remember from last time, if the overall limit exists, that means it agrees from both sides. Now we're just going to look from each side. So this first one means as x approaches c from the right. See that little plus on that c? So the limit as x approaches c from the right, from the positive side, and the one below it means as we approach c from the left. So let's go ahead and find this one-sided limit. Find the limit of the square root of 16 minus x squared, pictured there, as we approach 4 from the left. Let's do it graphically first. From the left. So let's approach 4. 1, 2, 3, 4. As we approach it from the left. So notice as we approach 4 from the left, we're approaching 0, right? Now, notice we can still plug it in, and we'll actually get a value. 16 minus 16 is 0. Square root of 0 is 0. Okay, but it has just a one-sided limit as we're approaching it from the left. Notice there's nothing on the right, right? So we can only approach this from the left. Let's do this next one here. Find the limit as x approaches 2 from the right. From the right. So we've got 2 minus x over x squared minus 4. You know, if we were to graph this, I would actually go, let me write this as negative x minus 2. Notice that's the same as 2 minus x over, and I'm going to factor this, x minus 2x plus 2. So I've got a hole there at x being 2, right? And this thing behaves like y equals negative 1 over x plus 2. And so I've got a vertical asymptote at negative 2. Got vertical asymptote negative 2. So instead of being up here, right, that negative, we'll flip that about the x-axis. So we actually end up being down here, and this one up there. And then at 2, I've got a hole right there. Okay? So I've kind of got the picture of this thing. And as I approach 2 from the right, so I'm approaching 2 from the right, and I can see I'm approaching a value, right? And of course I can't throw 2 in because I'm dividing by 0 into the original, right? But I know algebraically it behaves, or I'm sorry, graphically it behaves exactly like the simplified form, y equals negative 1 over x plus 2, except that one doesn't have a hole in it, right? So I could just throw it in and find the value. So let's throw it in. So it's going to be approaching negative 1/4. And again, you can see that, right, it's approaching that hole from the right, right, as x approaches 2 from the right. Which, by the way, it's also approaching that from the left as well, right? So the overall limit as x approaches 2 is also negative 1/4. All right, so let's see if we can't find some limits algebraically. Similar to finding an overall limit, we're going to see if we can't just plug it in, substitute it in, and get a value. So we got 1 over 1 plus 1 times 1 plus 6 over 1 times 3 minus 1 over 7. Looks like I end up with 14 over 14, which is 1. So this one-sided limit. Sure enough, you can just plug it in and it'll be okay. Now the question is, what about if we get a 0 on the bottom? Well, that's similar to this up here, where you're going to have to manipulate that thing algebraically. All right? So let's do some more one-sided limits. Let's do these things visually for a minute, and we'll get into some more discussion. All right, our functional value at 0 here. What's our functional value right there? Looks like it's 4. F of 2, notice f of 2 has a hole, so the functional value at 2 is undefined or does not exist. How about f of negative 2? Well, notice at negative 2, you see I have an orange there, that vertical asymptote. So f of negative 2 is also undefined, right? I have a vertical asymptote there, so there's no functional value. F of 4. F of 4 right there in green, it looks like that ends up being 2, right? Now let's do some limits. Let me erase these. Limit as x approaches 2 from the right. From the right. Limit as x approaches 2 from the right. So again, I'm going to follow this graph from the right. And it looks like I'm approaching that y value. It looks like it's a y value of 1/2. I know it's not defined there, but I am getting arbitrarily close to that 1/2 right there. So that limit exists from the right. From the left, x approaches 2 from the left. It looks like it's also approaching that same y value of 1/2. I'm getting arbitrarily close to 1/2. So do they agree? So the overall limit as x approaches 2 from the right and from the left, do they agree? And I would say yes, they do. So it's also 1/2. Limit as x approaches 0 from the right. Let's approach 0 from the right. You see in blue, looks like that ends up being 4 if we approach 0 from the right. As we approach 0 from the left, let's do that in green. As we approach 0 from the left, it's like it's 1/2. So the overall limit, do those two agree? No, they don't, right? There's a big gap there. They don't agree from the right and from the left. So the overall limit does not exist. The overall limit as x approaches 0. How about the overall limit as x approaches negative 2? Now look at this. As I approach, let me erase this. As I approach negative 2, notice as I approach negative 2 from the right, it's shooting me up. So technically it does not exist. We would describe that as going to infinity. As I approach negative 2 from the left, it's also unbounded. So technically the limit does not exist either. We describe that as negative infinity. They do not agree. So this does not exist. All right, here's some special trig limits that we're going to give you. Limit as theta goes to 0 of sine theta over theta is 1. We're going to use that first, and then there's some other ones listed as well that we'll use. And this is just another form of that first one. Limit as theta approaches 0 sine k theta over k theta equals 1. So if I'm looking at this, limit as theta approaches 0. Notice I can't throw 0 in for theta because I'd be dividing by 0 on this, right? So I'm going to use this special trig limit, the one that I have in blue up there. And I'm thinking to myself, well, what I want is that one in blue, or actually, this is a more simple form I can use right there. Limit as sine theta over theta. So notice I have just a 23 right there. That's just a constant. So let me rewrite that. Limit as theta approaches 0 of 1 over 23 times sine theta over theta. Now I know with my properties of limits, I can put this constant out front. And so this just ends up being 1 over 23 times the limit as theta approaches 0 of sine theta over theta. And I know this is 1, right? So I've got 1 over 23 times 1, because that's a special limit right there. And so this answer just ends up being 1 over 23. That's our limit on that. So that's using a special limit, that one in red there initially. All right, let's look at this one now. Notice on this one, it's not like I can take out that 8 right there, right? I'm stuck with that thing inside. Of course, that 5 right there, I can take out a 1/5, but that's not going to help me a whole lot. So what I'm going to do is I'm thinking about using the one in blue, limit as theta approaches 0 of sine of k theta over k theta is 1. Okay. And so what I want is I want this to be an 8 theta, not a 5 theta, right? And so what I'm going to do is I'm going to go ahead and, here, let me rewrite this. Let's rewrite this. Limit as theta approaches 0. Let me take the 1/5 out for a minute. So I have sine of 8 theta over theta. See how that's still the same thing? And so what I want here is I want to have this be an 8 theta, right? I want those and those two to be the same. Well, I can't all of a sudden just give it an 8, right, on the bottom. So I got to give it an 8 on the top. Multiply the top by 8. So I'm multiplying this by 8 over 8, or 1. Okay. So now we have, let me rewrite this. Limit as theta approaches 0 of 8/5 times sine of 8 theta over 8 theta. And then I'm going to go ahead and put this constant in front. And so I've got 8/5 limit theta approaches 0 of sine of 8 theta over 8 theta. And again, we know this is 1. That's a special case. And so this just ends up being 8/5 times that 1. And so our limit here is 8/5. All right, I'm looking at this next one. I'm like, okay, that's not any like sine theta over theta or sine k theta over k theta, right? I've got a 1 minus cosine over. So let me go back up here and let's look at which one of these can be useful. Let me erase that one for a minute. And I'm thinking to myself, all right, let me use this or this, right? So let me go ahead and write that down. So yeah, limit theta approaches 0 of 1 minus cosine k theta over k theta. This equals 0. So this is the one I'm going to try and use here, right? And I'm recognizing can be useful. So let's rewrite this as limit theta. Well, actually, let me go down here. Limit theta approaches 0. I'm going to take that 1/6 out. 1 minus times 1 minus cosine 3 theta all over theta. Now again, I want 1 minus cosine 3 theta over 3 theta, right? Over 3 theta. I've already taken this 1/6 out. I'm going to put that in front. So I just want a 3 theta right there. I can't just all of a sudden introduce it. If I multiply the bottom by 3, I got to multiply the top by 3, right? And so we've got, and I'm going to multiply the 3 times 1 over 6. So 3/6 or a half will be out front. And so this just ends up being a half. We know this whole thing is 0. So I got a half times 0, which just ends up being 0 on this one. I'm looking at this, you guys, and I'm seeing like That's 1 minus cosine 2 theta over 2 theta. So I'm seeing a special case right there. And then I'm seeing, because this is a common denominator, sine of 3 theta. Now I wish it was over 3 theta, but it's not. But I can manipulate that, right? There's another special case on that. So I can split these up. Limit theta approaches 0, 1 minus cosine 2 theta over 2 theta plus limit theta approaches 0 of sine of 3 theta over 2 theta. Now this we know is 0. Let's go down here and we'll write that. So we've got 0 plus, and now I'm manipulating this one, limit theta approaches 0. Let me take that half out, sine of 3 theta over theta. And we need that to be a 3 theta, so let me introduce it. I'll give it a 3 on the bottom, which means I'm going to multiply the top by 3. And then I'm going to take that 3 halves out front. So we've got 0 plus 3 halves, limit theta approaches 0 of sine of 3 theta. Oops, that's a really bad 3 theta. 3 theta all over 3 theta. We know this is 1. So we've got 0 plus 3 halves times 1, which is just 3 halves. Now in this one, what you want to do is you want to factor, if possible, anything out, both in the numerator and denominator. So let's see what happens if I factor stuff out. I'd have limit x approaches 0. I can take a sign out of both terms in the top there. And on the bottom, I can take a 3x squared out. And I'd have sine squared x plus cosine squared x. There's the old Pythagorean identity. We know sine squared plus cosine squared is 1, right? And so what we've got here, limit as x approaches 0, we got sine x times 1 minus cosine 3x all over 3x squared. Right? Now what I could do, remember 3x squared is x times a 3x, right? So what I could do is write this as limit as x approaches 0 of sine x over the x times 1 minus cosine 3x over the 3x, so that I can see my special cases there, right? Now notice I'm multiplying this, so I can split this up, but they got to be multiplied when I split this limit up. Limit as x approaches 0, sine x over x, there's my special case, times limit as x approaches 0, 1 minus cosine 3x over 3x, and I don't even have to manipulate any constants or anything, right? I've got my two special cases. This one's 1, this one's 0, so we've just got 1 times 0, which is 0. This limit ends up being 0. Thanks so much for watching. Take a note. See you next time.